Welcome. Today we're going to talk about generative adversarial networks, or more commonly known as GANs. GANs, as the name suggests, are yet another generative model. So let's recall just what we mean by generative model and what our goal in particular for this specific generative model will be. Our goal will be, given some data set, which is generated according to some probability distribution, we're going to want to generate more data from the distribution. Now, this is not always our goal when we're working in a generative modeling setting. For example, we may instead want to actually try to estimate P itself, like have an explicit description of something like that. But at least you can generally think of our goal with GANs as to generate more data from P. Now, the problem is the fact that P might in fact be complicated to describe, let alone sample from. So how are we ever going to be able to generate more data from P? Well, our solution is very similar to what we did last time with variational autoencoders, in the sense that the way we get around the complicated, the fact that P may be very complex is, well, let me just write this, I guess. The problem is that P may be complex. And the solution, like I said, is similar to what we did last time, where we just really, it's the same thing we've done for a lot of this class now. We'll simply let a neural network do all the work for us. So what we're going to do, the way we're going to solve this, is use a neural network to map basically starting with a standard normal Gaussian n0i, and these are mapped to samples from P. And so, like, in another way of saying this, similar to how we did last time, we say that if we have Z, which is sampled according to N0 identity, then we're going to want to learn a neural network, which is T sub theta. So theta will be our parameter vector for some neural network T, which will take in Z and a sample from like this distribution, and this will be distributed as P. That's kind of our goal. So let's kind of draw a picture, which is, again, this should all be kind of review in the sense that this is similar to what we did for VAEs. But the way you can the picture you can have in your head is we're going to have some Z here, some input Z, where Z maybe is distributed as N0 identity. And we're going to have output here. This might be a multi-layer network, but I'm just going to draw it as a single layer network just for brevity. So something like this. And so there's a neural network. There may be some nonlinearities, maybe multiple layers and so on, but it'll produce some vector X, where X is T of theta of Z. So yeah, this is roughly the type of picture which is very similar to the second half of a variational autoencoder, where it maps latent vectors, which are generated according to a Gaussian, into vectors which may be more interesting. I drew this where the latent space Z is only 3-dimensional and this is, say, 5-dimensional. That might not be the case. In fact, I believe often for GANs you might have a latent space which is even more higher dimensional compared to the output space. But anyway, overall, this is a this is the type of thing that we're going to want as our sort of final goal in order to generate samples from. And in the context of the GAN, this object here, which takes in samples, which are just Gaussian noise, and outputs sort of maybe more meaningful objects. This here, overall, this object here, this like little network that we're going to have here, this is going to be called the generator. The reason is that GANs are going to have two main components, and one of those two is the generator. So good. Yeah, our final goal is going to be, in order to solve this generative modeling question, is can we generate a network like this, which takes in Gaussian samples and outputs samples which look like this distribution P. So now how do we do that? How do we force this network to learn how to do this mapping and how to do this transformation. How to make this work. Well, this is kind of the core question in a lot of generative modeling questions, and for VAEs, you might remember that what we did, we basically we stuck another thing over here, which looks something like this, and we had to say that it takes in whatever input, and then it can map it truly to the Gaussian, and then it maps it back to itself. So roughly speaking, we with the VAEs, we had to enforce that it can encode and then decode itself. That is, given an input, it should be converted to some latent vector, which is Gaussian distributed, and then converted back to the original vector itself. That's roughly what we wanted VAEs to do, and by looking at that type of optimization problem, then we could solve the generative modeling problem in terms of making it so that this component itself was good. Because remember, in the end, what we really want is just to make sure we have some sort of generator which can do something like this. Now, it's going to be a bit different for GANs. We're still going to try to get something like this, but the way we're going to do this is we're going to basically see, we're going to phrase it as a type of classification problem, basically asking whether samples that we generate in this way, are they distinguishable from samples that we actually drew from the distribution itself? So you can think of it as a type of hypothesis testing question, where there's going to be another component here, which is going to take a look at samples and see if it can predict whether they came from this sort of fake data that we generated according to via the generator, versus being from the original distribution. So we'll say this a bit more in depth, and that's going to be kind of the main point of this lecture. But just succinctly, the idea is that GANs are going to make sure that these samples here are indistinguishable from real data. And it seems intuitive enough, right? That's essentially what we'd want to do. We want to say that this distribution, when we sample from t theta d, we want this to be approximately equal to p. That's like our ideal goal. We're obviously never going to get there because that's kind of hard to do, but that's our target. And what better way to say that these two are as close as we can get if there's no way to really distinguish samples? Like, we do this process and we get a bunch of data, and then we do just sampling from the original thing and we get a bunch of data. If we can't really tell the difference, then are they any different? Now, of course, we're not going to do it like that. For example, maybe there's some pictures which look very, maybe the distribution of pictures may look similar to a human, but it's not clear how you'd actually do that in a in sort of a training procedure. So instead, what we're going to do is we're going to basically use the fact that neural networks are actually very good at this type of distinguishing and, in fact, classification problems. So what we're going to do is we're going to have another neural network which kind of fights against this generator, which is known as the discriminator. The idea is this discriminator is going to take in samples which are from either this process here, they're either the output of the generator, or they're from the original training data set, and it has to be able to predict which ones are real, that is from the distribution P, versus fake, that are from the generator. So let's do this in a bit more depth. We're going to use another NN to classify real versus fake. Okay, so let me try to draw you a picture here. Okay, so what basically the picture you should have in your mind is, here is our generator. I'm just drawing it as a box. This is basically the same picture here, but I didn't want to draw as many lines, and it'll be a bit cleaner. So I'm just going to write it as generator, or gen for simplicity. And we're going to have z, which is n0 I. And here as an output, we'll have some sort of x tilde. This is just going to be some sample from the distribution, or sorry, some sample from n0I mapped through this network here. Versus here we have, say, our real data set. And this will just pick some arbitrary item out of it, some maybe random item out of it, x. So this is, just to say, this is a fake sample. And again, I call these sort of fake because they're trying to imitate this real data in the sense that it's supposed to look very similar. And so this is going to be a real sample. And the idea is that there's going to be some other network here, like yeah, there's just going to be another neural network. I'm not going to draw it in the same way I have before, but which is called the discriminator. And what's going to happen here is that it's going to have to basically output. It's going to take in an input, either say x tilde or x, and then it has to output fake or real. So basically it has to, even when the discriminator is going to be a type of neural network or some sort of network that, given either one of these x tildes, one of these fake samples, on those ones, so if it's given something that's generated according to this procedure and it's given an x tilde in, then the goal is for it to say fake. It's trying to correctly classify those as being generated via this process. Whereas if it's given a point from this data set here, the real training data, then it should be trying to say real, because it would identify correctly from being those two sets. So yeah. Let me just write that. The goal is to distinguish between t theta of z. So these are fake samples. Versus, say, samples from P, which are real samples. And the intuition is, and this network here, like I've used this, I've called this, what is it? I've called this, say, T of theta. Whereas this one here will be S of phi. So again, S is going to be our network, and phi is our parameter vector for this network. Good. So that's roughly at a higher level going to be the goal. I haven't told you a lot of things yet. For example, I haven't told you exactly what the loss function is going to be. In fact, we're going to derive that, how we're going to like set up the loss function, how we're going to train this, and stuff like that. But hopefully the idea of the different components and how they fit together should make sense. There's one component here, the generator, which is trying to generate fake data, which looks like the real data. And at the same time, there is a discriminator, which is trying to tell whether the data is real or fake. So now you can see how these two different components are kind of fighting against each other, in the sense that, for example, if the generator was able to somehow perfectly imitate the real data, then it doesn't matter what type of discriminator you have here. It would make no difference. It wouldn't be able to tell the difference between x versus x tilde if the generator is a perfect generator, that is, it can totally imitate the distribution, and therefore the generator would kind of be the victor and the discriminator would have no choice. On the other hand, you could imagine that maybe your discriminator is absolutely perfect in the sense that it can sense any minuscule difference between the data set coming out of the generator versus the data set which is the real the real data set. So yeah, that's kind of the sort of game that we have here. It's a game in a certain technical sense as well, but yeah, and in some sense, these each give information to each other. Like for example, if we have a discriminator which is very, very good, that is, it can tell which ones are real or fake by using the same sort of optimization that we've done before, for example, gradient-based optimization, that will give us some sort of idea or hint as to how to make the generator better. How can it isn't fooling the discriminator now. Well, maybe we can use gradient-based optimization in order to figure out how to improve the data that the generator is making to make it look more like this. And at the same time, if the generator manages to make things that really fool the discriminator, well, we can use the fact that we know which data is real and which ones are fake in order to help train the discriminator and have it do better. So, okay, so that's kind of the main idea behind this type of setup. Yeah, I think I've belabored this enough where, yeah, there's two players trying to either derive, one player tries to generate fake samples and the other player tries to tell which ones are the fake and real ones. Okay, so the question you might be wondering here now is I've given you a fairly intuitive or like high level explanation as to what's going on. You might have some pictures in your head as to how you might set this up. But let's, I haven't been technical at all in terms of telling you what actually happens and how you'd optimize this really. So let's delve into that. So I warn you, we're going to go on a little bit of a detour in deriving this loss, but it'll all bring it back. And at the end, when we come up with a good loss function and the type of thing, maybe we'll inspect it a bit closer in order to see how this is a reasonable loss function for this problem. So let's see. Deriving the loss. Now, in terms of deriving the loss, if we want to see why this is a reasonable thing to do, the first thing we're going to do is introduce a tool known as the Fanshell conjugate of a function. And what is the Fanshell conjugate? This might seem a little bit unmotivated for now, but let's see how we'll see later and get back to how it's quite useful. So let's let f, which is some function from, let's just say r to r. You can consider multivariate versions of this, but we're just going to focus on a one-dimensional problem for now. One-dimensional function. Let this be some function. And the Fanshell conjugate of f is the following. We're going to use this f star notation. So f star of x is the Fanshell conjugate of a function x. And this can be written as the following. It can be written as max over y of x y minus f of y. So yeah, this might seem a little bit odd. It's a strange function. Why do we use this? Why do we look at this? Well, I'm just going to introduce it for now, and there's going to be a property later that lets us that's very nice of it. But let's do an example first. I just introduced this property of a function, a transformation of a function. So let's see an example. And an example is we're going to take a look at the function f of x equals x log x. And what happens if we take the Fanshell conjugate of this? Let's just do it. So if we do f star of x, just plug it into this expression here. So it'll be max over y of xy minus y log y. So that's the Fanshell conjugate written like this. But this, of course, isn't very useful because we can't tell what this is not a very nice closed form function. So what we're going to do is the usual thing when we want to solve a maximization problem. We're going to take the derivative and set it equal to 0. So we're going to say d by dy of this quantity xy minus y log y. This is equal to x, and then taking the derivative of this, that's going to be minus log y minus 1. And we're going to set it equal to 0. And just rearranging, that is putting log y on the right-hand side. That'll give us that log y equals to x minus 1, which if you just take the exp of both sides, then you'll get that y is equal to exp of x minus 1. Okay, so we found the y which optimizes it, which will maximize this function. So let's just plug it back in. And we get that f star of x is equal to x times exp of x minus 1 minus x minus 1 exp of x minus 1. Well, just noticing that this term and this x here cancel out, this is just going to be exp of x minus 1. Cool. So we have derived the Fanshell conjugate of this x log x function and shown that is equal to exp of x minus 1. So that might seem, okay, so why did we do this? Well, let me just be patient with me and let's keep going, actually, in the sense, what happens if we take the Fanshell conjugate of the Fanshell conjugate? There's nothing too difficult about this in the sense that we can always do it again. Well, what happens, and I'm just going to write it like this, f star star of x, this is going to equal to, just apply the definition again. Recall the definition is max of y over y of xy minus f of y. Well, we can just do that again. Max over y of xy minus exp of y minus 1. And then we take the derivative, d by dy of xy, exp of y minus 1. This is equal to x minus exp is its own derivative, so exp of y minus 1. Let me put this down a line. And we want this to be equal to 0 because we're trying to again find the maximization of this. And we get that this implies that, what do we get? We get that log of x equals y minus 1 just by moving this over to the other side and taking the log of both sides and rearranging a bit. That gives us that y is equal to 1 plus log of x. Good. So that gives us the value y, which will optimize this. So let's just continue here. This is going to be equal to x times 1 plus log x minus exp of, well, you can see what happens here. It'll be, just sub this in, 1 plus log x minus 1. And if you do this, it'll just become minus x. So this is equal to x plus x log x minus x, which is equal to x log x. That's our final answer. That is the Fanshell conjugate of the Fanshell conjugate. So if you take the conjugate twice, notice what happens. We got back to exactly where we started. So that's quite interesting, and that's actually the main property that we're going to use. Again, you're probably wondering, why did we go off into this notion? Well, the main claim which I will write here is that, I'm not going to prove this, but the claim is the following. F is convex if and only if we have that f double star, that is the conjugate of the conjugate, is equal to the function itself. So what does that mean? That means if we have that a function is convex, then we can always just double conjugate it and then get back to the original function that we started with. Now, this might seem kind of useless, especially since we did these calculations here, but we're going to see why this is useful when we represent the loss function for GANs. Okay, so that is Fanshell conjugates. In short, they are an operation you can apply to a function, and if you apply this operation twice to a convex function, then it'll give you the original function back. That's basically the main thing to get out of this. Another tool we're going to mention is that of F divergences. So now F divergences, you have already seen them before in the sense that they're ways of measuring the distance between two distributions. So let me write out what the definition of the F divergence is. D of f p q is equal to the integral of q of x times f p of x divided by q of x dx. And we need that where f is strictly convex, and that we need f of 1 is equal to 0. So yeah, hopefully you remember the definition of convexity, what it means for a function to be convex. Well, we're going to need that our function f is going to be strictly convex. And furthermore, if you plug in 1, then it's going to be equal to 0. And yeah, we'll see why in an example in a second, why this sort of f of 1 is equal to 0 is helpful. But the main idea is that this measures distance between two distributions. And if the two distributions are equal, well, naturally that distance should be equal to 0. So suppose you take p and q to be the exact same. Well, in this ratio, then we'll have that p of x is equal to q of x, and therefore this term inside here will become 1, and therefore the whole thing will become 0. So this is kind of useful in terms of setting, making it so that if the two are the same, then it's going to be equal to 0. But let me give you an example of an F divergence, which you've actually seen before. So say we're going to use the function f is equal to, let's say, f of t is equal to t log t. Then we would have that the divergence between p and q, f divergence, is going to be equal to the following. Q of x, and then we just plug in this times log of that. That would be times p of x over q of x log p of x over q of x dx, which is equal to the integral of p of x log p of x over q of x dx. And you might recognize this as just being precisely the definition of the KL divergence, which I'll just write as KL, between p of x and q of x. So yeah, this is all this to show that the F divergence, it can simulate the KL divergence, which is perhaps the most common distance measure between probability distributions in machine learning. But you could also plug in different functions and it might behave somewhat differently. But yeah, at least you can see that it encodes the KL divergence, so it must be some use at least. Okay, and let's prove something very simple about this notion of F divergences. Well, a very simple thing that we can show for this is that if p is equal to q, then this is always going to be equal to 0. And let me do this. So the claim is the following: that d of f p with respect to q is going to be greater than 0 and is equal to 0 if p is equal to q. And this is for in general, not with respect to this specific f, but just for general f divergence, which satisfies the sort of requirements. We need to be strictly convex and equal to 0 when f when you plug in 1. And so this is the following. Let's see. The way we'll prove this is very simple. I just want to get you comfortable with this. So if we just write out this, then we're going to have q of x times f of p of x divided by q of x. And by applying what's known as Jensen's inequality, or maybe you've heard it more often as Jensen's inequality, which basically says that for convex functions that you can essentially do this. You can pull, if you have a convex function, then you can pull the function outside of the expectation if you're taking the expectation of a function like this. So essentially it lets you pull this expectation out, and then you get integral of q of x p of x over q of x dx. And this is going to be equal to, well, if you just cancel these two terms out, then you're taking the integral of px dx over the entire domain. And so this whole thing here will just be 1, just because you're integrating a distribution over its entire support. And what else did we say? We say that f of 1 is equal to 0. Let me note that this shows the first part of the claim, that this quantity, this f divergence, will always be greater than or equal to 0. Let me just say, sorry, yeah, that's greater than or equal to 0, in fact. So it's always going to be greater than or equal to 0 because the left-hand side is greater than or equal to 0. And how about the second part of this? How do we show that it is equal to 0 if p is equal to q? Well, this is fairly simple. We can show this just by noting the fact that if p is equal to q, then p of x divided by q of x is going to be equal to 1. So integral of q of x times f of 1 dx. Well, this is equal to integral, because we use the fact that f of 1 is equal to 0, then this will just be integral of 0 dx, which is equal to 0. So, and that's with equality. So yeah, that's the claim. Just showing you a basic fact of this. And with all this out of the way, we've sort of built up a few different tools here, which we're going to put it all together now. We've built up these tools of f divergences, which are measures of distance between probability distributions. And we have Fanshell conjugates, which again are just sort of an operation you can apply to a function. And if you apply it twice to a convex function, you get it back. Well, let's finally go back to GANs and see how this is useful. So let's recall what our goal is with GANs. Our goal is really to get our density. Goal is that get density q of theta to be approximately equal to p. So I'm just using q of theta to represent the distribution or the density function, which is over the sort of same domain. Let me say, I want to be precise about this, so let me try to say what I mean, just to recall that we let t of theta of z. What we said before is if you feed something into z, then this is sort of a function of t of theta of z is a function which maps this to a different domain. So what we're going to say is that q of theta of x is the density function of point x where the random, where there's the density function. Yeah, it's a density function of at a point, sorry, density function, let me say, at x of the random variable defined as follows, where we first draw z generated according to a n0i, and then and output t sub theta of z. If this was getting a bit maybe like too precise, but really what I just wanted to make sure that there's no confusion. This is really the density of the outputs when you draw something from the latent space and then push it through this generator neural network. So yeah, our goal is really to get the density of that process to be approximately equal to the density of P, which is the true density. So okay, if we're trying to get these two densities to be close to each other, well, that's really, that's essentially what we can do using F divergences. In particular, our goal can be, let me restate it, or a way of realizing this goal. This is not precise, but a more precise way perhaps of saying this goal is we want that minimize over theta d of f of p of x with respect to q theta of x is our objective. And we'll just say for some f, in the sense that we have to specify which type of f divergence we want to optimize, but we'll get back to that later. So yeah, really our goal is to try to find the theta which makes the true distribution as close as possible to our distribution of fake samples. So again, in this formulation as is, forget totally about the discriminator, because again, our goal when we're doing this type of generative modeling is not really to do some sort of weird discriminator stuff. We're really just trying to get a generator, because that's our final goal. Recall, let's scroll back up to the top. Our final goal is really just to get one of these things which will map Gaussian samples into samples which are kind of from the distribution. So that's our final goal, but we're going to see by just manipulating this objective function, which doesn't have anything to do with our discriminator, we're going to see how manipulating this will give us something which has a discriminator very naturally. Okay, so good. Yeah, so the main thing we're going to do is we're going to essentially put these two detours I took you on together. That is, put the F divergence here together with the Fanshell conjugate, and we'll see how something nice pops out without too much trouble. So let's just write this loss function right here, d of f of p of x, q theta of x. Let's just write this out. This is, I might drop the subscript just because it's more natural. But you should keep it in mind that there's a distribution that's a density that's parameterized by this theta. Q of x. And what we're going to do is we're going to use this claim that I mentioned about Fanshell conjugates. So remember that if a function f is convex, then it implies that taking the Fanshell conjugate twice is going to be equal to itself. So this is perhaps the trickiest part of this derivation I'm going to do here. But the main thing is that we're going to rewrite this f right here as the conjugate of its conjugate. So let me do the step and then we'll discuss it a bit. Okay, this is the big step, which is perhaps the least clear. So let me say what exactly I did. Well, like I said, in the case where we have an f to be convex, which is going to be in the case for this, because when we're dealing with an f divergence, we're always going to deal with an f function which is strongly convex, in fact, which is even stronger than convex. Well, the observation we can make is that f is equal to f star star. So f is equal to f star star. So now how do you write f star star? Well, f star star is equal to, as we sort of discussed earlier at some point, let's say t, this is equal to, sorry, let me write it with a bit more space. Note the fact that f star star of t is going to be equal to max over s of s times t minus f star of s. And you'll notice that's exactly what we did here when we're trying to write the Fanshell conjugate of the Fanshell conjugate. We just took this f, we used the fact that's equal to f star star, and then we wrote this f star star in terms of just the definition of the Fanshell conjugate. So you can see here this term in the square parentheses, that's just the substitution right here. You can see this t here is p over q of x, and maybe the difference here is the fact that instead of just doing some fixed number s, we're now taking an s which is parameterized by x. Because the way you can see this is that we're really taking the Fanshell conjugate with respect to every point simultaneously. So in other words, each individual point can have a different value of s, which is multiplying it. So that is the main idea. So hopefully think about the step and make sure you followed it. But after we do that, it's fairly easy. All we have to do is just rewrite and rearrange this a little bit. We'll just do the following. We'll just sort of pull this max out. So what we're going to do is we're going to pull this max out. And here, while it was with respect to a specific point, s of x is just, remember, is parameterized by x in the sense that it's going to try to find the max for each individual point. Well, if we pull it out, then we not only need it to get the max for every point, but we're going to need it to be, it's no longer going to be parameterized by x anymore. So it's going to be a max from r to the d to r. And then it'll be of following integral of q of x times, sorry, p of x. So just taking the first term here, then this q of x and this q of x will cancel out. So we're going to have p of x, s of x times dx. And then the second term here, we're going to have minus integral of q of x f star of s of x times dx. And that's basically it. Yeah. So yeah, again, I just want to emphasize really that since we don't have sort of x in scope anymore when we're doing this, then we have to find the s which maps from which maximizes this. It can be an arbitrary function really, but it's some function which maps from points in x. That is the sort of space that we're trying to find a density over, and it maps each different value to a different real number. And that will kind of realize this Fanshell conjugate in terms of the definition. And as one final simplification, let me just write it in a way which I think is which is more concise. So max over s, which map from r to the d to r, of the following. So note that this is just the integral with respect to some density p of x of s of x. So we can just write that as an expectation, where x is distributed as p of x minus the expectation of f star of S of X, where X is distributed as according to Q, and I'll put in this data again here, of X. So yeah, this is kind of an aesthetically pleasing way of looking at it. Why is that? We're essentially going to look at the max over all possible functions, and we're going to take the difference between the expectation of that function when we draw a sample according to the true density P, and we're going to subtract out some transformation of that function where the sample is this time drawn according to some other distribution Q. Yeah, and one way to read this is kind of saying that S is the function that makes this difference as big as possible, because remember, we're going for max, so we're going to try to make this as big as possible and this as small as possible. And another way of saying this is, note that the first thing we have here, this is essentially looking at the value when you're given a distribution, a sample according to, like, for the sake of this discussion, at least pretend this F star isn't here. We're not going to, I'm going to sort of ignore that for now. But one way of saying this is, imagine you got a sample from P, then you want to show that the value of you want to find a function where the value of that function is large when you get a data sample actually generated according to P, but it's small when you generate it according to Q. So now maybe this seems familiar, right? Because what is P here? P is going to be the true data distribution. And Q of theta, that's going to be our fake data distribution. So maybe this starts coming full circle in the sense that we're going to look at one expectation when we're looking at the true data, and another expectation when data is drawn from this fake data set. So this is actually where the whole idea of these GANs comes in the sense that right, you can think of this S as being a function that distinguishes between these two types of samples. And so then, therefore, this S is really going to be the neural network, which is the discriminator. So let me try to write this. Let's take a step back and kind of look at our again, our optimization problem that we were looking at. Our optimization problem we were looking at is something like the following. We are really trying to find the parameter vector theta, which makes these two densities be as close to each other as possible, while using this type of derivation that we did here, where we just took the Fanshell conjugate of itself, of F, and did it again. Then we can say that after all this, that this is approximately equal to min over theta, and that's just using what we had out here, and then just doing this transformation, then max over all phi of the following quantities. Px s phi of x dx minus integral q theta of x s, or sorry, f star s phi of x dx. So, okay, this is actually, so this is now just writing it in terms of the thing that we've already looked at, in the sense that this s phi of x, this is going to be our discriminator network. And we can just put it right here. You'll note that this might be a bit different from what we looked at before, in the sense that before what we were looking at was the max over all possible functions s. But here we're restricted in a little way, because we're not going to look at all possible functions s. We're instead going to look over all possible functions. We're going to try to optimize over all possible functions that can be parameterized by a neural network, because s phi of x is going to be some sort of neural network. Nonetheless, it seems to be like it's not ideal, but it's still pretty good. And just like neural networks worked in almost every other situation that we've looked at, well, they'll also work here in the sense that it'll let us get around the fact that we're not actually optimizing over all possible functions. But yeah, neural networks are good enough. Okay, so this is essentially the loss function that we want to optimize when we are doing when we're training a GAN. But the thing is, these integrals are kind of hard to, we can't really optimize these integrals empirically. So instead we just do it via the usual sort of Monte Carlo / averaging over our data set approach, where we are just going to do the following. So we just do the same thing. And what we have here, let me write the loss function. Yeah, this quantity right here. And let me try to interpret this. So one thing that you might have been bugging you all this time is the fact that we still have this f star here. Well, we're going to get rid of that pretty soon, but just take my word for it. Whenever we instantiate this, remember, we're going to specify what specific function where we want to optimize. Like, we're going to specify our f divergence. So if you specify which f divergence you're trying to optimize, and different f divergences will lead to different types of GANs and different types of results, but we're going to specify our f nonetheless. And once you specify that f, then this f star will be easy to like calculate. You know, we did one of these calculations before. So no matter what f divergence we look at, we can always come up with an f star here. So that's no problem. Yeah, and now let's try to interpret these terms that we have here. So the way we interpret this is, I haven't told you everything here, but this term here is these points are going to be the real data. And this expression right here, this t sub theta of zj, this is going to be our fake data. Where I guess I haven't, let me just be clear about this, that the zj's are going to be distributed as n0 times the identity, or n0i, where j equals 1 to m. So the idea is that we're going to just generate a bunch of fake data in order to feed into our network, and this 1 through m here, that's going to be our real data, which we're also going to feed into this. So yeah, that is going to be our loss function, and you can see that we sort of minimize over, let me write it like this maybe. Well, no, this minimization problem corresponds to the generator, in the sense that notice how we have this theta here. It's just used here where we're trying to generate this fake data. So that's our what the generator is trying to optimize. And meanwhile, this here is a discriminator, in the sense that our discriminator is going to be this s of phi, and we're trying to optimize the parameters in order to maximize this quantity. So like I said, we're going to really have a sort of game where you can picture this as a game where both of the two players, or the generator and the discriminator, they pick some data and phi respectively, and they try to one is trying to maximize the function, the other is trying to minimize the function. And yeah, if you can find, yeah, the goal is to basically try to find a saddle point of this type of thing. But okay, this is still a little bit more abstract. Let's try to get it very concrete, where you'll have like literally a loss function that you could plug in and try to optimize yourself. So this is just generically what we're looking at for an arbitrary f divergence. Well, let's look at a specific f divergence, and we'll come across the loss function, which you will most often see when you're looking at GANs, or at least in most of the time in sort of basic applications. And we have what's known as the, let me write it out fully, I guess, the Jensen-Shannon GAN, often known as the JS GAN. Yeah, there's pretty much infinitely many different GANs in terms of you'll see them with all sorts of letters in front. But here JS GAN means the Jensen-Shannon GAN, and it's where it's basically something very similar to let me write it like this actually. It's something very similar to the KL divergence, but it is actually a little bit nicer in certain ways, in the sense that it is symmetric. So it's this plus KL of Q with respect to P plus Q over 2. So you can see here, unlike the standard KL divergence, this is going to be symmetric. So this is a nice and natural way of measuring distances. And so that's the Jensen-Shannon, I guess this is the Jensen-Shannon divergence, but this is the, we'll derive the GAN for this. So this is going to be the, just trust me, I haven't actually even told you what the function f is to arrive at this, but trust me when I say that the f star, which corresponds to it, is going to be minus log 1 minus exp of t minus log of 4. This is going to be the f star function, which corresponds to this Jensen-Shannon GAN. This we can actually turn out to just ignore, just because it's going to be a constant. So you can just imagine if you had an additional constant in this term in the summation, well, there's nothing you can do to change that, so we can just ignore it. So yeah, and then we're also going to, the final trick we're going to do is also reparameterize so that we basically replace s with log of s. And this is going to be very nice because you see here we have this log 1 minus exp of t. Well, if we take the log instead, then it'll just be 1 minus t essentially. So, okay, all this work aside, just take a look at this expression and convince yourself that if you do these sort of things here, that is plug in this f star of t and do this reparameterization, then we will be able to arrive finally at the following type of loss function. So we're going to try to minimize, maximize over SV, and we're going to have the following here. Okay, so this is probably what you most often see as the GAN loss function. And yeah, let's parse through this and see if we can interpret a little bit, and to see how it really corresponds to this intuitive description which I gave you sort of towards the beginning of this lecture. Yeah, I mean, the way you can see it is, first of all, let's focus on the two different parts of this. Yeah, I mean, let's sort of fix this, fix the t theta. That is, we're going to fix the generator, and we're just going to look at what the discriminator is trying to do. If you take a look at this, what this discriminator is trying to do, it's essentially trying to solve a type of logistic regression. Now, this is with a non-linear logistic regression, but if you just look at the fact that you're summing over the points which are, say, summing over some points, and these are going to be like you're summing the logs of these, and then you have log of 1 minus these. Just if you look back at the logistic regression objective function, then this is really essentially the same thing for a fixed t. If you just imagine these are sort of fixed samples and you fix t and the mapping of them. So yeah, you can picture S as trying to solve a type of logistic regression classification problem. And meanwhile, T of theta, you can see that essentially when they're doing their optimization, then the former term just drops out because it's not really relevant, because the only thing which has parameters that they can affect is here. And you can see that essentially they're trying to optimize this in order to fool the discriminator as much as they can. to really minimize the chance that they're correct. Yeah. Maybe you can see that by the fact that what is this classification? S is going to be a function which outputs something in the range 0 to 1, because it's going to be some sort of classifier trying to pick whether things came from either the true data or the fake data. And clearly the goal of what it's trying to do is say that things which came with the fake data is going to be equal to it wants to really find that these things are equal to 0. That's corresponds to its goal of trying to maximize the overall quantity. But if somehow the T manages to fool it, it's really trying to make S phi think that these points should be classified as zeros, as ones, because if it can get it to think that they should be ones, then this will be 1 minus something close to 1, and therefore log of that will be very large negative number. So therefore that will be correspond to minimizing this. So yeah, hopefully picturing these two things one at a time and looking at what each different network is trying to do here should help you understand what's really going on here and how this corresponds to the picture that I drew above. So let me just draw that in fact again, where we have here, this is our generator, and you can call this like T, generator T, and then we have the discriminator S, I'll even write in the parameters here, and then these are sort of, we have Gaussian noise here, 0 I, this fed in here, and then we have real data, it's fed in here, and the question is which one is fed in, and then this has to guess whether it's either 1 or 0 versus 0 equals fake. And again, hopefully you can see how this sort of corresponds to this loss function here, where kind of the discriminator is trying to make sure if these points come in, that does well in this term, and simultaneously at the same time making sure for the data which comes in through this path, it does well here. Whereas on the other hand, the generator is really trying for these points here, which are fake, that it really wants to get them to come across as real. So it's trying to make this mistake here, make the discriminator make a mistake here, which will minimize this term over here. So yeah, you can see how, hopefully how the full story goes through. This is the sort of story I told you of what's going on here, and you can see how it maps through to the math. So make sure you really understand how this corresponds to the math, because I think it's quite beautiful and important. Okay, so after this is how you train. This is the type of thing that you do in training again. You really try to optimize this. We'll talk about how to optimize this in a sec. It's kind of challenging and often. But after you've done the training process, what you can do then is just look at essentially this box right here, because it's similar to how we did it for VAEs. What you do is just disconnect the discriminator. You can throw it out. It doesn't really matter anymore. But what you do is you just feed Gaussian noise into the generator, and then it'll pop out new samples which are different. Cool. So that's what GANs are really. And in terms of optimization, this is like the last question. How do we optimize this? Because you know how to train like a regular neural network in the sense that you have a loss function where you just try to say minimize something. But here we're going to have two different things. We're going to try to simultaneously minimize with respect to some parameters theta and maximize with respect to some other parameters phi. So it's not clear how exactly to do that at first glance. There's maybe many different ways of doing this. But the idea is just, well, there's many different ways to do this, but the way I'll tell you is like gradient descent ascent, which is essentially with the min player, what you're going to do is optimize these parameters by taking a gradient descent step. And at the same time, you're going to try out for the max player, you're going to optimize their parameters by taking a gradient ascent step. So this might not be clear. So let me try to write it down a bit. So the main thing is simultaneously update phi and theta using gradients. And let me just write this down, like just to be really clear about what I mean by this. So we update phi. This is going to become phi of t plus some learning rate eta, and we'll in fact let the learning rate eta be different for both the phi and the theta player, so to speak. You just take the gradient here, and you take the gradient of this loss function here, log x phi of xi. Let me be clear that this is s of t of xi plus 1 over m summation of log 1 minus running out of space here. Okay, but yeah, this is hopefully good. All right, want to be unclear here, so let me just write this. Okay, so this is the objective for the gradient update that we would do for the phi, in the sense that it's literally just a standard gradient ascent step. So why do we do gradient ascent? Well, recall that this phi, we're trying to do a maximization here. So when we want to do a maximization, we do a plus instead of a minus. And at the same time, what we're going to do is we're going to also update the theta parameter. And we do it kind of at the same time. I'll explain what I mean by that. So I'm going to simplify this by noting the fact that when we're taking the gradient with respect to theta, this former term doesn't have a theta in there anyway. So we're just going to drop that term entirely and just focus on the latter term. And we have this right here. So let me just try to explain what is going on here. Well, you can see that here we're just going to do the same gradient descent step we do normally. The important thing to note is the indices on these different parameters, in the sense that the way you should picture this is both of these steps are made at the same time. In the sense that you can see that we take the gradients with respect to the parameters at time t, and we update both of them to t plus 1 based on the things at the previous time step t. So if it were sequential, then maybe we would update this one, and then this would be with respect to t plus 1. But no, we do them both at the same time is kind of a canonical way of doing it. But there's many variations, of course. For example, you can take multiple steps with one parameter first, and then you take a step with the other parameter. Or you can maybe alternate them so that they don't happen simultaneously. Or you can even look at previous time steps, which turns out to be better for optimization in some parts. Yeah, optimizing GANs is notoriously difficult in the sense that they can be very finicky to some of these parameters. So just be aware of that. And you can run into many problems when you're doing things like this. In particular, if you just change some hyperparameters a little bit, then maybe before it converged, but after you do something like this, then it doesn't converge. And yeah, so always be careful when optimizing GANs and be prepared for a little bit of frustration, let's say. Okay, so this is everything I wanted to say about optimizing GANs and the formulation and everything, but maybe why does everyone talk about GANs? What are these good for? Well, let me provide you with some applications and show you really some of the magic about GANs and what they are capable of. So I've got some pictures here. The first one here is these people here. Well, these people don't actually exist. These are incredibly high quality images of people who never exist. And this is a figure from the sort of Style GAN 2 paper, which is one of the better GANs in terms of producing quality images. This is in a paper by Karas et al. From, I think, just last year. And you can see these are surprisingly high fidelity and quality images that look like real people. If you squint very hard, you can really tell some ways these don't look quite perfect. For example, this guy's facial hair here is a little bit asymmetric. It's not quite perfect. It would just be his style, I guess. And the background here doesn't really make a lot of sense. Like, what is this going on here? But yeah, this is nonetheless, I think, fairly high quality, high resolution images, which are quite diverse. So this is kind of like the major success story that people talk about when they say GANs at first. Like, it can generate really cool pictures, which are of people who don't exist. So that's kind of cool. But there's more than just that. There's other things, of course, going beyond just the standard GAN setup that we talked about in this lecture. People have been looking at a lot of ways to modify it and other tricks you can build on top of it. Well, let me show you this. These here are from a paper by Reed et al. This is a text to image, a text to image kind of problem. So the idea here is that the GAN, what you do is you give the GAN some text, like this small bird has a pink breast and crown and black primaries and secondaries, and given just this text, it can manage to produce these images which are of whatever this is describing. And similar for all of these cases. So this is kind of cool because, you know, normally GANs are just supposed to produce good quality images, but somehow this also says, okay, it has to produce some cool image, but conditioned on this being a pretty good description. So it has to actually do something involving both language as well as images at the same time. But nonetheless, it can kind of draw a picture of whatever you're thinking of. And this is actually a few years old now, so there's better things which can do things like this now. What else is there? What else can GANs do? Another useful and interesting application is something like this, where essentially it can do super resolution, or if you've seen any sort of crime drama, you know how sometimes they say enhance the picture. Well, maybe you thought that's impossible, but in fact, it's kind of possible in the sense that it can't. GANs can help you interpolate and really scale up pictures in terms of resolution. For example, this is an image, an original image, and this is a high resolution version of the same image. It's kind of weird seeing it drawn at the same size, but trust me, when the original image had kind of more pixels in it, sorry, this image here, it had more pixels in the sort of version that they generated. So yeah, GANs are good at kind of interpolating and really resizing images much better than other sort of more primitive ones, which you may see. So yeah, do I want to say anything more about that? Yeah, not so much. Okay, and just as a couple more examples of what else can be useful, it can be useful for image-to-image translation. I kind of think of this as style transfer, which is something a little bit different, but it's kind of thematically similar, and I feel like a little bit more evocative to say that. But for example, given some sort of image like this is a black and white image, well, it can somehow learn how to fill in the colors and do some sort of colors. And given this picture, which is a daytime image, it can generate this picture, which is the same image except at nighttime. Similarly, if somebody just drew a picture of a handbag like this, then it can figure out what the real handbag should look like in terms of like putting some textures on it. So this, I think, is really cool because yeah, it can translate image to image. And this is from a paper by Isola et al. And as a final application, I will show you this picture, which is kind of cool, kind of like a little bit technical as to what's going on inside a GAN. Well, by using these kind of latent representations of what's going on in some of these things, what you can do is say start with this person, a man with glasses here, and you can see kind of what a man without glasses looks like. Well, if you subtract these in an appropriate sense, which I won't get into, then essentially man with glasses minus man without glasses, that should be equal to glasses. And if you add on a woman without glasses, that'll give you a woman with glasses. So this might seem kind of nonsensical, but it actually works pretty well. You can see here that we have a woman with glasses by doing these weird sort of additions and subtractions in the appropriate space. So this is from a paper by Radford et al. Yeah, and this is just a few of the examples of the power of GANs in the sense that they can do lots of pretty cool things like this. And other things which, yeah, for example, if there's certain applications involving where you draw in an image editing program, and based on what you've drawn, it can suggest kind of how to complete the drawing. So yeah, they're very, very good at generating images generally. Like these really work for any type of data sets, but I think the most striking examples and applications involve image data for the most part. Okay, so that's basically everything I wanted to say about GANs. They were kind of a very hot research topic a few years ago, and they're still, I think, very popular in terms of applications because they can produce very high quality fidelity and high fidelity data. Kind of a bit better than, yeah, non-trivially better generally than variational autoencoders as well as other types of generative models. So these are some of the best generative models we know of right now.